Hello everybody, and welcome to a video in my absence about chi-square tests. We're getting towards the end of chapter 2, so if you look in your textbook, the sections aren't numbered obnoxiously, but there is a section called chi-square tests. It's towards the ends of chapter 2. This is still firmly within the hypothesis testing realm, so we're still going to be testing claims against observations and seeing if we believe the background claim or not. I guess I should say that I really like this particular method, this chi-squared thing. It's close to my heart because one of my favorite academic papers I ever wrote was a chi-square paper with one of my students 4 or 5 years ago, a data science student. We were looking at some election data and doing chi-square tests on it. It's pretty fun. So if you want to see that, I might show it to you in class, highlights of it. Anyway, so what are these about? Now, chi, I guess I should say chi. That's the Greek letter chi. So sometimes people write it out like that. It's pronounced chi, not chai. It's not a T. And here's the actual Greek letter. So some texts write out the Greek letter. Sometimes they write CHI. So a chi-square test is a kind of hypothesis test involving frequencies of categorical data now. So this is different from what we've been doing. And categorical data just simply means you have data in different buckets, like colors. Like you could have red, green, yellow kinds of candy. You could have different days of the week, and then you have counts of those things. So these two examples here are the kind of sort of universe that chi-squared tests deal with. So here, these are both just made up, but whatever. So here's the first example. The Skittles company claims they produce an equal amount of purple, red, orange, yellow, and green Skittles. That's what they claim. Now, why would they do that? You know, purple and red are obviously the best. Nobody likes orange Skittles, do they? Nobody likes yellow. So what they should be doing is making more purple and red. But they don't. They claim they make it an equal number. So what you do is you take a random sample of 200 Skittles for science. And if the claim is true, that they produce an equal amount of each color, then out of 200, I mean, there's 5 colors, you would expect 40 of each color. That's what you would expect given this background claim. However, your observations are this: 20 purple, 23 red, 48, 42, 64. Well, that's quite a bit different from a 40, 40, 40, 40 split. So, as always with questions like this, you're not allowed to just say, wow, that's different from what I expected, so I guess the claim is false. So, do we have actual statistical evidence based on our sample that the Skittles actually aren't produced in equal quantity? So there's an example of a categorical count data, frequency count. 23 from this category, 48 from that category, and we're expecting 40 from each category in this example. So here's a second one. So we know a person's birthday is likely to fall on a Monday, Tuesday, Wednesday, so on. There's no special birthday day of the year. So suppose you're overseeing a survey where you're gathering a bunch of information about people in the sample, and you're worried that one of your students is making up data to save time. And you notice that among all the data you've gathered, there are 100 people. They've all been asked, hey, this year, what day is your birthday on? 15 say Monday, 8 say Tuesday, 35 Wednesday, and so on. So you were expecting an equal number-ish per day, right? So about 100 divided by 7 or so. But that's not what you see here. You see 15, a 36, a 1. The data's all over the place. So the question is, do we have strong evidence that these numbers deviate too much from what we expected? Chi-square tests investigate things like this. So it lets you test observed counts of categorical data against some background expected distribution of counts. That's what it exists to do. The test outputs a test statistic called a chi-square value, and like every hypothesis test, a p-value. The p-value is basically measuring how well, as always, it's measuring how well your observed data sort of conforms, or is consistent with some sort of null hypothesis background claim. The chi-square statistic is calculated like this. You're not going to be doing it by hand, but I still want to show you the formula so it's not a black box. So suppose you have n categories. So think of each category as a color of Skittle or a day of the week or something. You could have up to n categories. OI is the number of things you see in your data in category I, and EI is the count that you expect in that category. So back here, O1 would be 20, but E1 would be 40 if our first category is purple. The chi-squared statistic is calculated like this. For each observation, you subtract the expected amount that you expected to see, you square that value, and then divide by the expected amount, and you do that over and over again. If you like this sigma sum notation, that's all you're doing. And notice that all you're doing with these differences here is you're just measuring sort of the distance from what you see to what you expect. So if what you observe is exactly what you expect, then a term like this becomes 0, and your chi-squared value in the end would be 0 if all of these line up. So a chi-squared value of 0 means you see exactly what you expect. So the bigger the chi-squared value is, the farther what you see is from what you expect. So if you want to see a sample calculation to understand that formula, for the Skittles example, we saw 20 of red and 23 of purple. I forget the exact colors, but we saw 20, 23, 48, 42, 64. We expected to see 40 each time. And so for each of these fractions, you take this expected value here and copy and paste it down in the bottom. So this denominator here has to match this value here. In this case, the 40s are all the same. That doesn't have to be the case in other examples, but anyway, if you calculate all this out, you get a chi-squared value of 33.23. That's very much not 0. So we did not get, like our observations did not match up with what we expected. But the question is that really big or really small or what? Like, what does that even mean? So if you've never dealt with these tests before, and I assume you haven't, there's no reason to know what that means. But I can tell you, when I saw that value, I thought, whoa, that's humongous. So chi-squared values of this big are very large, meaning we have strong evidence that what we see and what we expected are very different. Okay, so a chi-squared test, it then takes your test statistic and the number of categories that you have. So the statistical method does depend on number of categories, kind of like, the stuff we've been doing depends on the sample size. So the test, the more categories you have, the test reacts differently to it. But in the end, it gives you a p-value. And as always, the lower the p-value, the less the observed data conforms with what we expect. And so more formally, in a chi-squared test, like the ones we're doing here, these are technically called chi-squared tests, goodness of fit tests. That's what we're doing. But anyway, the null hypothesis is the data I got comes from data that looks like some sort of background distribution, like uniform distribution. Everything is all the same. That's what we were doing here. If the background distribution is correct of equal number of Skittles per category, we would expect to see 40, 40, 40, 40, 40. And then what we actually see is 20, 23, 48. So the null hypothesis is that the colors are equally distributed, and then we compare our sample to that expectation. So the null is like, my sample comes from a background distribution that looks like what I expect, and then the alternative is like not that. So if you get a big chi-squared value, that gives you a low p-value, letting us reject the null, and the null is that basically the background distribution is what is modeling things here. I haven't shown you how to calculate this, but I would just tell you in the Skittles example, the p-value is extremely small, 0.000054. So that lets us reject the null that Skittle colors are uniformly distributed. Like, if Skittle colors were uniformly distributed, then in a sample of size 200, it'd be really rare to see something like this. You could just get super lucky or unlucky, depending on if you like greens. If you like greens, I guess you're lucky here, but it is possible by chance to get a distribution like this, these 5 numbers, but that chance is pretty small. It's way less than 1%. So that's how a chi-squared test works. So the other example we did was with birthdays on a day of the week. So we know from background information, from background observations, that you're just as likely to have a birthday on Monday or Tuesday or Wednesday, whatever, this year. And then so suppose you're overseeing a survey where the graduate students are giving you these numbers. Like, hey, I took a sample of 100 people. These are just the numbers from before. So what I would like you to do is calculate the chi-squared value on your own. So make sure you can do this. So even though we're not going to do this much, it is sort of an exercise in understanding where the chi-squared value comes from. And if you do that, let me point out that the expected outcome for each day, so we have 7 days of the week, there are 100 people. And so the expected number of people per day, birthday per day, is 14.29. And so your initial reaction to that might be, that doesn't make any sense. I can't have 14.29 people tell me their birthday is on Monday. I can't have fractions of people. And I would say to you, like, yes, that's of course true. You can't have fractions of people, but this is really supposed to be kind of an average. So if you took a bunch of samples of 100 people over and over again and asked them, how many of you have a birthday on Monday this year, then the average value would be 14.29. And that makes sense. When you start to average these whole numbers, you can get a fraction. Anyway, so I want you to calculate the chi-squared value for this example using this expected value for each category and the numbers that we have up here, 15, 8, and so on. So you can pause the video and do that if you want to. And now let me just show you. So here's what we observed. It's helpful to make a table like this. Here's what we observed. Here's what we expect to see on each day, 100 divided by 7. So if you do 15 minus 14.29, square it, divide by 14.29, add 8 minus 14.9, square, so on. You do the whole thing. You get a chi-squared value of 98.5, which is like crazy high. So, I mean, kind of obviously, this list of 7 numbers is like nothing like this list of 7 numbers. So something's pretty screwy with this sample, I guess maybe your graduate student's not making stuff up, but there's something weird going on here. We have statistically strong evidence that this is weird. Okay, so in the 2 examples we've done, these expected frequencies, whether they be 14.29 or whether they be 40, they were the same. That's not always the case. So you can certainly imagine examples, which I have here on the screen, where the background expectations aren't all the same. So for example, suppose you sample people or survey people about how much they drive in a given year. So you say, hey, last year, how many miles did you drive last year? Estimate it for me. And you create categories like this, 0 to 4,000, 4,000, 8,000, so on. And then all the way up to 24,000 miles and above. The question is, well, what would you expect this data to look like? What would your background expectation be? And if we were in class, I would force you to give me some answers here, right? But if you ask me, I would say, well, I mean, most people who own a car are driving more than 4,000 miles. That's not very much, actually, right? If you have a job that you drive to, you're definitely driving more than 4,000 miles in a year. But man, 24,000 and above, that's a lot. So like these 2 categories should be pretty rare. Basically, anybody who has a job would be above this. But man, driving 24,000 miles in a year, are you a long distance trucker or something? What's the deal with that? I would expect most people to be kind of in this range here. So I would expect something not like this. So if you saw this, you'd be like, okay, well, wait a second. If this is the claimed data, 51 people drive between 0 and 4,000. That's the same frequency as people who drive between 12 and 16,000. I mean, does my sample have a ton of old people in it that don't drive? Is that why there's a 51 here? And then does my sample also have a ton of long distance truckers? Putting a 52 here. Like, why are these numbers all basically the same? That doesn't make any sense to me. So all I'm saying is, if you ask people, a random sample of people, right? You don't ask a bunch of old people. You don't ask a bunch of truckers. You take a random sample of people and ask, how much did you drive last year? You wouldn't expect to see data like this. You would expect to see maybe something like this. In particular, the average car owner, we know from previous data, drives about 14,000 miles in a year. So it makes sense that so I don't know if these numbers are exactly correct or whatever. I'm not trying to claim I know exactly what's happening here, but what you would expect is some kind of rise and fall. So the number up here These are like retired people or something who aren't driving very much, or people who live like super close to their job and only drive to the grocery store once a week. People like that. And then these people maybe are, I don't know, traveling salesmen or something, right? But kind of the average person is not driving less than 4,000, not driving over 24,000. So I would expect something like this. So all I'm saying is your expected outcomes, these counts in this expected column, they're not always going to be the same. It depends on what kind of data you're talking about. If you're talking about, birthdays on a given day of the week, then sure, they're the same. Like Monday and Tuesday are the same. There shouldn't be any difference. But if you're talking about miles driven, these numbers should be different. It'd be kind of weird if they are the same. And there was actually a very famous study. Ironically, it was about honesty and ethics. But the study asked people this question: how many miles did you drive last year? And the data looked like this. Very suspicious. Okay. So the paper was eventually retracted because people suspected the data was just made up. People suspected that the author just had Microsoft Excel generate random numbers in these bins and then do these counts. So this is not a toy example here. I have that study in mind when I made this example. So if you see this, man, that's suspicious. You should see something like this. Okay. So anyway, if you want to run a chi-square test like this, now that we've established what it is, in practice, you do not want to do this thing by hand every single time. That would be very tedious. Nobody wants to do that. Calculate this 33.23 or whatever you did by hand here. If you did this one by hand, you don't want to sit here and do this by hand to get 98.5. So what you're going to do instead is go to the Chapter 3 module on Brightspace. There's a file called something, Chapter 3 code. I wonder what I called it. Chapter 3 code chi-square. Yeah, Chapter 3 code chi-square is the file. You're going to grab that, copy and paste it into a notebook. This is the birthday example. So what you do is you just type, separated by commas, the observed values you saw in order, and then type the expected ones in order, like this. So like here, the expected ones are all equal, so the order doesn't matter, but make sure like this expected one corresponds to this observed one, and so on. But once you type your data in, you just click play, and it shows you the chi-squared value, 98.5. Shows you the p-value, 0. Okay. So way back here, where was it? Like if this is what you expect and that's your data, wow, the probability of seeing data like this with this kind of background expectation is 0. You would, if this is the expectation, right? Assuming the data should fit something like this, the probability of seeing data like this is 0, basically 0. Let me show you another one, the Skittles one. Where was that? Skittles, okay. So if you want to do the Skittles one, you just come back up here, type in the observations, so 20, 23, 48, 42, and 64. And the background or expectations were 40, 40, 40, 40, 40, like that. Okay, so now at least you get a p-value that's not 0, but that's really small. So if Skittles truly were uniformly distributed, the probability of seeing data like this is tiny. So something has gone wrong here. As long as you didn't screw up your sample, if this is a truly random sample, then you would reject the claim that colors are equally distributed. So in practice, this is what you'll use, this code. Get you a chi-squared test statistic and the p-value. Okay. Yeah, so something like this, if you wanted to test this, let me just show you how you type that in. So I have my observations, which are 51, 53, 49, 50, 54, 51, 52. Like I said, I don't know if this is exactly what you would expect, but you would expect some kind of bell curvy kind of behavior. So let me put this kind of bell curve behavior here. 90, 70, 40, 25. You just type both those in, hit run. It says, wow. It says no. No. Right, so there's this, no. Can't be right. Okay. So that's what you'll do in practice. Just type in like that. All right. So before you use a chi-square test, though, there are some things you should check. So I really cannot stress this one enough. I have seen chi-square tests misused a lot because I work in the election space, like the math and election space, and man, there are a lot of people misusing chi-square tests. And often what they get wrong is this first bullet point. So I put this in bold, and I'm really screaming this at you, right? If you want to use a chi-square test, you have to be very confident that you understand what that background distribution should be. Now, sometimes the claim is just made and you're just testing against it. So like with the Skittles one, they made this claim, right? They claimed that the colors are equally distributed. So that 40, 40, 40, 40 is them saying, right? And you're just testing against their claim. But sometimes like, you're making a claim. Like here, to run a chi-square test for real, I would need to have a pretty good idea what these numbers should be here. I would need to really know that miles driven follows a normal curve. And if I had a sample of this size, there's like, how many people? Like 350 people or something in the sample. I would really need to know if I had 350 people that these are what the numbers would be. So before you run a chi-square test, you have to know what kind of thing you're expecting to see. And that needs to be on very firm ground. Because if you don't actually know what you're expecting and you choose to expect something that's like arbitrary or something, you're just going to get it wrong. You're going to make silly claims. So that's the first thing. You have to understand deeply and confidently what the background distribution is before you measure deviation from it. Okay. To use the test we've been using, your data must be counts or frequencies from categorical data. Generally speaking, there's no hard and fast rule here, but your expected counts should be like 4 or 5 or maybe bigger. If your expected counts get really small, then the test gets kind of iffy. It's kind of like having too small of a sample size or something like that. So you want to make sure that like here I didn't have any issue. My expected numbers were all way bigger than 5 or 4. But if these numbers start getting too small, you should be less and less willing to run a chi-square test and make conclusions from it. It's also worth pointing out that your expected frequencies, your expected counts, must add to the size of your sample. So like these numbers here, they're not fixed. If I had more people in my sample, these would get bigger. Like here, like this 14.29, that's there because I had 100 people in my sample. If I had 200 people in my sample, this would be like a 28 point something. So this is a common mistake students make sometimes, is like they forget that these numbers have to add up to the sample size. So like this column and this column both have to add to the sample size. Okay. So I want you to try this example on your own, but let me read it out real quick. So consider a slot machine. If you don't know what a slot machine is, let me show you. I don't know how many of you people are running to the casinos after class or whatever. So a slot machine, it looks like this. It's not going to let me zoom in. Whatever. You can kind of see. It's bigger. It looks like that. You pull a lever and then these wheels spin. In this particular slot machine, there's 3 wheels, but other machines have more than 3. It just depends on what you're playing. Like this. Pull the lever, these wheels spin. The wheels have symbols on them, and you win if after the wheels are done spinning, all the symbols match. That's how you get the biggest jackpot. And if the symbols don't match, you don't get anything. So you pay $5 or something to pull the lever. That's what a slot machine looks like. And these wheels, they turn independently. So like the first wheel doesn't know what the second wheel is doing. So on. Okay. So consider a slot machine with 4 wheels. Each wheel has, say, 5 symbols on it. I don't know what the standard number of symbols is, so I just chose 5 arbitrarily. So you pull the wheel or pull the lever, all 4 wheels spin. When the wheels stop, if all 4, in this particular setup, I'm just making up a slot machine here. If all 4 wheels show the same symbol, you win a jackpot. If 3 of the 4 wheels match, you get a smaller prize. Otherwise, you get nothing. Let's say that's the parameters of the game. And then I would just tell you this. So you don't need to know where these numbers come from. I just calculated them myself. If the wheel were fair, the probability of winning the jackpot is 1 in 125. Probability of winning the smaller prize is 80 in 625. And the probability of winning nothing is almost 50%. 112 out of 125. So the owner of the machine worries it's been tampered with. So to test that, she pulls the lever 600 times, gets 8 jackpots, 81 smaller prizes, and 511 no wins. So the question is there strong evidence that the machine was tampered with? That's not fair. So if you want to, you can pause and do this entirely on your own. But notice that to do this, I have observed data for 3 categories. Jackpot, small prize, no win. I have these 3 counts. To run a chi-square test, you have to figure out, well, what do I expect to see actually, right? Like this 8, do I expect to see 8? Do I expect to see 81? If so, this isn't suspicious at all, you know? So if you're going to do this on your own, you should think about what the expected counts should be. So you can pause and think about it. But anyway, if the probability of getting a jackpot is 1 in 125, and then you do 600 spins, probability times number of spins is what you expect. So if you spin the wheel 600 times, on average, you'll win the jackpot 4.8 times, basically once out of every 125 times. And if you spin the wheel 600 times, on average, you'll win the second prize 76.8 times. And then on average, you'll get nothing 537.6 times. So if you want to run a chi-square test on that, let's see, come back here. Oh, I already have it typed down here. Okay. So my observations were 8, 81, 511. My expectations are, as it shows there. So if you do this, the chi-squared value is 3.6-ish, and the p-value itself is like 16%. Okay, well, 16% is bigger than 5%. So even though, you know, this looks kind of suspicious, I guess, like you expect 5 wins, but you got 8. You expect 77. Second prize, you get 81. You know, what you see in the sample is bigger than what you expect, but it turns out it's not that much bigger. So I guess it's suspicious on its face, but until you run the math, you don't know how suspicious it is. A p-value of whatever it was, 16%, that's not super low. That's okay. So, I mean, it might be the case that the wheel has been tampered with, maybe, but we don't have strong evidence that it was. That p-value is not small enough. Okay, so that's an introduction to chi-squared tests of goodness of fit. Does our observed data, do those counts, do they fit what we expect? And when there's deviation from what we expect, how much deviation is okay? And at what point do we get so much deviation that we reject a background claim, right? In this case, the wheel was fair. In this case, our background was that the distribution was normal. What we see is not that at all. So we would actually accuse somebody of making up these numbers, you know, like this doesn't make any sense, you know, so on. Okay, so if you have any questions on this, please let me know. When I get back, we'll do some more problems on this. And where we're headed next actually is more kind of thinking about detecting fraud. So here's an example where we could say we think we found some fraud. If somebody reports data like this, you know, that's pretty suspicious. So when we get back, we'll cover something called Benford's Law, which is used all the time to catch things like accounting fraud, or at least it used to be. So back in the 90s, there were some big cases where it was used like that. Okay, let me know if you have any questions.